Welcome to Lecture 40, 12.1 Goodness of Fit Test. So we're nearing the end here. Determine critical values for the chi-square distribution. So we use the symbol, and we have somewhat of a sort of nice scripted x squared, which you call chi-squared, not chi squared, chi-squared, to represent the values of the chi-square distribution. Critical values for these are found in Table 8. Which is in the back of your book, or it's in the Tools and Resources section of your MyLab Statistics. So what are some of the characteristics of the chi-square distribution? Well, number one, it is not symmetric. Okay. The shape of the chi-square distribution depends on the degrees of freedom, similar to the student's t distribution. So it's similar, not the same thing though. And 3, as the number of degrees of freedom increases, the chi-square distribution becomes nearly symmetric. So as the degrees of freedom increase, it'll slowly start to look more like a symmetric curve. And 4, the values of chi-squared are non-negative, or greater than or equal to 1 is another way of looking at it. So note, we use the notation chi-squared alpha to denote the critical value such that the area under the chi-square distribution to the right of alpha, to the right of alpha squared, chi-squared alpha, is alpha. Alright, let's take a look at example 1. Find the critical value such that the area under the chi-square distribution to the right of the critical value is 0.90. And we have two options, assuming 3 degrees of freedom, and then we'll look at assuming 5 degrees of freedom. Okay, so go ahead and look in your table and try to see if you can determine these just looking at table 8. I'll go ahead and bring it in right now. Okay, so we have a small portion of table 8. We have the degrees of freedom, and then this is for the chi-square distribution. So what are we looking at? Well, we want to look at distribution to the right of the critical value, and our table is given in terms of the right. So we're looking for 0.90, which is going to be right here, this column. And then what are we looking at? Well, we're looking at 3 degrees of freedom. So 3 degrees of freedom is going to be along here, and aha, where do they intersect? Right here at that value, 0.584. So how would we answer this? Well, we're going to have the critical value is chi-squared of, and our alpha here is 0.90, of 0.90 is going to equal 0.584. So let's take a look at the next one. Try to see if you can find that one out for yourself. Now we're looking for 5 degrees of freedom. So go ahead, follow along on that row until, we see where they intersect right there. So the critical value is chi-squared, and our alpha in this case, it's still the 0.90. It's going to be equal to 1.610 with 5 degrees of freedom. Okay, so note, as the degrees of freedom in table 8 get larger, some values are no longer going to be included in the table. What does this mean? Well, notice right now it's going by 1, 2, 3, 4, 5, 6, 7, and so on. After a point, it'll start jumping, so it'll be like 40, 50, 60, 70, 80, and so on. So when this happens, choose the degree of freedom that is closest to your degree of freedom, which is usually the case. If you don't actually see your value on the table, choose the value that is closest. 2. Perform the goodness of fit test. So we want to find a way to be able to test hypotheses regarding a probability distribution. Alright, so by definition, a goodness of fit test is an inferential procedure used to determine whether a frequency distribution follows a specific distribution. So expected counts. I'm sorry the screen's a little crooked. My page looks crooked. I just haven't been able to figure out how to make it tilt back. Alright, so looking at expected counts. Suppose there are n independent trials of an experiment with k greater than or equal to 3 mutually exclusive possible outcomes. Let p sub I represent the probability of observing the first outcome, and e sub I represent the expected count of the first outcome. P sub 2 represent the probability of observing the second outcome, and e sub 2 represent the expected count of the second outcome, and so on. So that's just how you're listing out the values. Alright, so then the expected counts for each possible outcome are given by e sub I equal to mu I, which is equal to n times pi, so n times the probability, where we have all the different values, the first one, second one, third one, and so on until we hit k, the number that we're looking for. Possible outcomes. So 2. Determine the expected outcome, or the expected counts for each outcome. Well, how do we determine the expected count? Well, we're going to go ahead and use the formula given right up here. So the formula states e sub I is going to equal m, or mu sub I, or n times p sub I. So for our expected count here, this is going to be 1 for I, this is 2, 3, and 4. So this will be e sub 1, which is going to be equal to n times p sub 1. And I'll go ahead and write down the formulas for both of these, or sorry, for all of them. Okay. And here we have, so e sub 1 is going to equal, well, n doesn't change for all of these, it's still 500, but the p-values change. For this one, it's 0.2. And calculating that out, we'll have 500 times 0.2, which is 100. So that's the expected count for that one. And then the expected count for the other one will be 500 times 0.1. For this one, it will be 500 times 0.45. And lastly, 500 times 0.25. Alright, go ahead, pause the video, try to calculate these out by yourself. We get 50, and then 225 and 125. So those are the way to find the expected count, which we'll be using for the test. So the test statistic for the goodness of fit test. Now that's a word to say. Well, let O sub I represent the observed counts of the category I, and E sub I is going to represent the expected counts. So one thing we'll definitely be doing in this section is you'll be looking at the expected account based on what you have for your information, and then what is actually observed. You're going to be comparing those two. And the counts of category I, and K is going to represent the number of categories, and N will represent the number of independent trials. Ooh, squished that in there. Of an experiment. So then what do we have? Well, the test statistic, chi-squared, is going to be as followed. The sum of the observed minus the expected divided by the expected value, n squared. And this is for all the values of 1, 2, up until k. So for all the different number of categories. Not too bad, you're just taking the subtraction. So how would we do that here? Well, we would do the observed, whatever we had, and subtract from 100, and so on. So just subtraction, division, and then summing it up, which we've done before. So this approximately follows the chi-square distribution with k minus 1 degrees of freedom, provided that, so here we go, these are the things we need to check. All expected frequencies, are greater than or equal to 1, and no more than 20% of the expected frequencies are less than 5. It's kind of interesting, but those two are the things to check. So now, once again, we are going to be having the classical approach and the p-value approach. And those basically just change how you're looking at the chart. So, step 1. This is the same step for a lot of them. You're going to determine the null and alternative hypothesis. After that, you're going to decide on a level of significance, usually given to you, depending on the seriousness of making a type 1 error. So now this is where the two tests sort of deviate from one another on step 3. Well, it starts to deviate on step 3. So for step 3, first calculate the expected counts, EI for each of the k categories, where we have E sub I equal to n pi, which we just did on that example, for I equal to 1, 2, all the way up to k, where n is the number of trials and pi is the probability of the ith category, assuming that the null hypothesis is true. Okay, so you'll be finding these assuming that the null values are true. And then step B, you're going to verify that all the requirements for the goodness of fit test are satisfied. Test. Ran out of space there. And 1. All expected frequencies are greater than or equal to 1. We already saw this. And no more than 20% of the expected counts are less than 5. Let me go ahead and fix that. So the test statistic, we're going to go ahead and compute that. It's going to equal, same thing for both of the approaches, for classical and p-value. Same way to find the statistic. Oh, this is between E, let me change that. And step 4. You're going to determine the critical value using table 8. All goodness of fit tests are right-tailed tests. So the critical value is chi squared alpha with k minus 1 degrees of freedom. And what are you going to do with that? We're going to compare that critical value to the test statistic. If we find out that test statistic is greater than the critical value, then we're going to reject the null hypothesis. Lastly, we'll go ahead and state the conclusion. So once again, you're going to compare the value that you computed. This is the one we compute right up here. We'll compare it to the value that we find on the table, which is from table 8. We'll compare them, and if the value we computed is larger, we reject the null hypothesis. So that is how we do the classical approach. So let's go ahead and take a look at example 3. We are given the following information. We have the null hypothesis of all the probabilities is supposed to be a fourth. That's the null hypothesis. And all alternative hypothesis is at least one of the proportions is different from the others. So the first thing we're going to do is fill out the expected counts for the given chart. Alright, one thing I've noticed is this is spelled wrong. Those guys are in the wrong spot. Okay, so how do we find the expected counts? Remember, expected counts, you're going to use the formula. Where'd it go? Ah, there we go. I'm going to highlight it in yellow. Right there. E sub I is going to equal n times p sub I, where p sub I is the probability of the ith category, assuming what? The null hypothesis is true. So we're going to assume the null hypothesis is true. So since we're assuming it's true, the probability we're using is going to be the 1/4. So the expected, so I'm going to go ahead and call these, well, actually, since they're already called A, B, C, D, we'll call these EA. That is going to be n times p. Well, what is n? we have to find n. N is going to be all of our values added up. So that'll be 30 plus 20 plus 28 plus 22 is going to equal 100. Okay, so we have n is 100, so this will be 100 times, and we're not going to be using the frequency. Okay, remember we're using the probability from the null hypothesis because we're assuming the null hypothesis is true, and that probability is a fourth. Let's go ahead and set it up for all the other ones. EC, I'll go ahead and pause the video and set these up. Alright, so the expected values, if the probability is the same for all of these, should end up all being the same, right? Because we're expecting the proportion to be a fourth for all of them. So we have the expected values and the observed values. Now we're going to go ahead and check the requirements for the goodness of fit to make sure they are satisfied. So what are the requirements for the goodness of fit? Well, we want to make sure that they're all greater than or equal to 1. Let's go ahead and check them real quick. What are the requirements? All frequencies are greater than or equal to 1, yes. And no more than 20% of the frequencies are less than 5. Well, none of our expected frequencies are less than 5. So we'll go ahead and just write this down in one fell swoop. We'll say all expected frequencies are greater than 5. So the requirements are satisfied. And that would work because it's covering both of the requirements. One requirement is everyone needs to be greater than 1. The other one is at least 20% can be less than 5. So because all of them are greater than 5, we can just say, you know what, they're all greater than 5. Don't need to worry about it. Awesome. So now we're going to determine the chi-squared test statistic. So that, let me write it out, is going to be the sum of our observed values minus the expected values divided by the expected values squared. Okay. What are our observed and expected values? Well, the first couple, or pair, we have 30 and 25. And remember, the observed are OI and expected are EI. So we're going to do 30 minus 25, square that, and then divide by the expected value of 25. That was the first one, so let's go ahead and add the next group, which will be the 20 and the 25. So we have 20 minus 25 squared divided by 25. Then plus the next group, which will be the 28 and the 25. So remember, it's always observed minus expected. So we'll have 28 minus 25 squared divided by 25. And the last group, we have the 22 and the 25. Once again, on your homework, you might have some larger data sets. Remember, on the exams, everything should be doable by hand. So you're not going to have huge data sets, because doing lots of number crunching on an exam is not that fun. Alright, so there we go. We have everything set up to do our test statistic. So I'm just going to go ahead and do some of the small work by hand, but remember, the main thing I need you to show on your exams are this step, your formula, showing the plugged in values, and if you went directly to the calculation, that would be fine. Those three are what I need to see. I'm going to go ahead and do an in-between step. So we'll have 5 squared divided by 25 plus, that's going to be negative 5 squared divided by 25 plus, and that looks like 3 squared divided by 25 plus, and that is, negative 3 squared divided by 25. So 25 divided by 25 plus 25 divided by 25 plus 9 divided by 25 plus also again 9 divided by 25. Remember, any negatives will be cancelled by these squares. These guys all go to 1, and we have 2 plus 18 over 25. And that's as simple as possible, so just 2 and 18 over 25. So that is our test statistic, chi-squared, and we'll be comparing this with the value that we see on the table. So because we're going to be comparing it with another decimal, I'll go ahead and translate it to a decimal as well. It comes out to 2.72. So easier to compare to the decimal from table 8. So now we need to determine the degrees of freedom. Well, what do the degrees of freedom come from? Let's go ahead and check our table here. Degrees of freedom are k minus 1, where k is the number of categories. Okay, so how many categories do we have? We have 1, 2, 3, 4 categories. So we're going to be looking for k minus 1, which is going to equal 4 minus 1. So that means we have 3 degrees of freedom. And you can go ahead and abbreviate with degrees of freedom. So we have 3 degrees of freedom. And now we're going to test the hypotheses using the classical approach at the alpha equals 0.05 level of significance. So I'm going to go ahead and bring in my table value once again. Alright, so now we have our table value. It's a little bigger because I'm including a few more values this time. But we are looking for alpha equals 0.05. So for alpha equal to 0.05, we're going to go ahead and look at this column here. And then we are using degrees of freedom 3. So 3 degrees of freedom, boop, right there. Where do they intersect? At this point, 7.815. Okay, so we found that chi-squared of 0.05 is going to equal 7.815, and we are going to be comparing this with our test statistic, which we found was 2.72. So how are we comparing them? Well, according to our steps, if our test statistic is greater, we'll reject the null. So which one is greater? Well, it looks like that value is greater, which is my critical value. And this is my test statistic. So if chi-squared, if that is greater than our critical value, then we reject the null. However, we have 2.72 is our test statistic, and 7.815 is our critical value, which is not greater. So that is not greater than. So what are we going to say? Well, because it's not greater than, we do not reject the null hypothesis. Since our critical value is less than, since our test statistic is less than our critical value, there is not sufficient evidence at the alpha equal to 0.05 level of confidence. To do what? To conclude that any of the proportions is different from the others. Alright, so there we have. You go ahead, you find your test statistic, which you calculate, then you look up your critical value and you compare them. If your test statistic is greater than your critical value, you can reject the null. Now, let's take a look at the goodness of fit test using the p-value approach. So once again, the first 2 steps are the same for for the classical and the p-value approach. It starts to get different on step 3 and forward. So first, determine the null and alternative hypothesis. Second, you're going to decide on a level of significance, depending on the seriousness of making a type 1 error. After that, you're going to go ahead and calculate the expected counts, E sub I for each of the k categories. And it's the same we had before, E sub I equals n times p sub I for I equal to 1 through k, where n is the number of trials, and p sub I is the probability of the ith category. Once again, assuming the null hypothesis is true. And B, verify that all the requirements for the goodness of fit test. And what do you know? I fit it this time. The goodness of fit test are satisfied. And 1, all expected frequencies are greater than or equal to 1, and no more than 20% of the expected frequencies are less than 5. Computing the test statistic, which is the same as the classical approach. It's just the sum of the the observed minus the expected squared divided by the expected. Now this is where it definitely changes from the classical approach. We're going to use table 8 to approximate the p-value by determining the area under the chi-square distribution with k minus 1 degrees of freedom to the right of the test statistic. And once we found that value, if our p-value is less than alpha, then we are going to reject the null hypothesis. And lastly, we'll state the conclusion. Okay, so usually, or pretty much actually, it's just going to be the very last step in step 3 and step 4 where this differs from the classical approach. Basically, just how you use table 8 and what you're comparing in the end. So let's take a look at example 4. According to the manufacturer of M&Ms, 12% of peanut M&Ms in a bag should be brown, 15% yellow, 12% red, 23% blue, 23% orange, and 15% green. A student randomly selected a pack of peanut M&Ms from Costco. He counted the number of M&Ms that were each color and obtained the results shown in the table. Find the expected counts for the table. And we need to determine n first. So the frequency, now these were the things he found, or the observed count. What we need to do is determine the expected count based upon the probabilities that M&M gave us. Now, in this case, which is different from the example we just did, the probabilities for the null hypothesis are actually different. The probabilities for the null hypothesis are given to us here, and we're going to try to determine if they're going to be different. So for the expected count, we have E sub, and this is going to be 1, 2, 3, 4, 5, and 6 categories. So you're comparing 6 categories, so E sub I is going to equal n times P sub 1. E sub 2, n times P sub 2, E sub 3, n P sub 3, and so on. So go ahead and try to calculate out what the n value is going to be for our problem here. Okay, so I calculated it out. Our n value is 400. Alright, so going ahead and plugging this in, we're going to have 400, but remember this time, the null hypothesis values are actually different percentages, and it's given in the above. So the null hypothesis value for brown is supposed to be 12% for brown. Okay. And one thing to note, there is a quick error here. So the red should actually be 12%. Let me go ahead and write that on the top. And the orange is actually supposed to be the 23%. Small error there. Okay, so, well, the percent for brown was supposed to be 0.12. And then we have the 400 times, and the percent for yellow is 15%. So 0.15. And so on. I'll go ahead and pause this, fill in the chart, and check back in with me in a second. Alright, so check your answers with mine. So that was the expected counts. Now we're going to go ahead and check the requirements for the goodness of fit test. And for those, we're just going to check that the expected counts are all greater than 5. If any of them are less than 5, we can only have 20% of them less than 5. Well, they are all greater than 5, so we can just say the requirements are satisfied because all E sub I are greater than 5. Now we're going to go ahead and determine the test statistic. Once again, write down the formula. We want our observed value minus our expected value squared divided by the expected value. Well, what are our observed and expected values? The first pair that we have is 53 and 48. So the observed is 53 minus the expected, which is 48, and go ahead and divide that by 48, and remember to square the top. Now the next pair we're looking at is 66 minus 60, and then we'll divide by the 60. And square the result there. Or not square the result, just squaring the top, not the whole thing. Next pair we have is 38 minus 48. Divided by 48 squared plus, go ahead and fill out the rest and check in with me in a second. Alright, so I went ahead and I found the other values, did the subtraction, and then we'll go ahead and plug these in and find the answer is approximately 3.568, and we'll go ahead and do 686 as after that. Why am I extending it that far? Well, remember, we're going to be looking at the table to find this value. And once again, in terms of grading, I'll look for that you put down the formula, you fill in the formula, and then you give the answer. Pretty much those are the steps that I'm looking for. Now, let's determine the degrees of freedom. Well, the degrees of freedom are going to be k minus 1, where k is our number of categories. So how many categories do we have? Well, we had 6 categories. So that's going to be 6 minus 1, which is going to equal 5. So our degrees of freedom, 5. Now we're going to go ahead and test the hypothesis using the Pvalue approach at alpha equals 0.05 level of significance. Alright, so this is where, once again, the p-value is different than the classical approach. So the first thing we're going to do for the p-value is we're going to look for the row that is our degrees of freedom. So the row that is our degrees of freedom is going to be 5. So that's the first thing we're going to do. Let me go ahead, highlight that. And in that row, we are going to attempt to search for our test statistic. So looking at these values, which value is closest to our test statistic? Well, our test statistic is 5.5686. So which one of these is closest to that? Well, it looks like the closest one is right there, the 9.236. You could go ahead and calculate that. That is the value that is closest to our 5.5. And the p-value that corresponds with that will be about there. But this is not perfectly our p-value. If you wanted to find the perfect p-value, you'd use technology. But once again, for the exam, we're going to be doing it by hand. So using technology, sorry, not using technology, just using the table, we have that our p-value is going to be a little greater than 0.10. Alright, so we found our p-value. The last thing to do is we're going to compare our p-value, scrolling back up, to our alpha, and then we'll reject it if it's less than it. So what is our alpha? Alpha is 0.05. But notice, our p-value is actually going to be greater than our alpha, which is equal to 0.05. So since it's greater than, we're not going to reject the null hypothesis. So what will our conclusion be? Well, our conclusion is going to be that there is not sufficient evidence at the alpha equals 0.05 level of confidence, significance, to do what? To reject the percentages given by M and M. Period. You could write a fancier sentence including all the percentages of the colors, but I would be satisfied with that type of a sentence. Alright, so note, last thing, whenever we are testing a hypothesis, the evidence can never prove the null hypothesis. to be true. We're just saying that we don't have enough evidence to conclude that the distribution has changed significantly. Alrighty, that is it for this section. So once again, remember, the p-value approach, you look in the table at your degrees of freedom, and then you find your alpha value up above. It is different for the classical approach. For the classical approach, you find the critical value using your degrees of freedom and the given level of significance. Okay, that is it for this section. Please email me if you have any questions.